Hi everyone! Welcome to Chapter 1, Section 2. We kind of skip over Section 1 of this book because it doesn't talk about a whole lot really. So starting with Section 2, we are trying to find limits graphically and numerically. So first question, what is a limit? When we write it out in math terms, it kind of looks like this. We have lim, to stand for limit. Underneath it says x, arrow, some number. That box is going to be some number. So we're basically saying when x equals whatever that number is, of this graph, so f of x is just, y equals whatever. So for whatever graph it is, or for whatever function it is, the y value when at that x value that we're asking about is blank. And that's a limit. So when you're finding a limit, the answer is always going to be some sort of y value based on the graph or based on the function itself. So in this section in particular, we're just going to be looking at two different methods to finding these limits, either graphically, using a graph, or numerically, using numbers. So first, let me give you an example with a graph. So here's our graph. This is the function f of x equals x cubed minus 1 divided by x minus 1. So if you remember from graphing your rational functions, this is a graph where there's going to be a hole because if we were to factor out the top, something would cancel out with the x minus 1 that's on the denominator, and that creates a hole in the graph. So as you can see, the hole occurs at x equals 1 and y equals 3, if you needed to know. But when we're looking for a limit graphically, if I were to find the limit as x approaches 1, so we're saying when x equals 1, our graph of f of x, which is the one that's graphed here, the y value here, so this right here, I'm trying to say like as you approach the graph from both the top and the bottom, going towards the x equals 1, the y value is 3. So the limit as x approaches 1 of f of x is 3. So in this example, I have another graph. So first I want to find the limit as x approaches 1 of g of x. So here's my graph of g of x. At x approaches 1, we're saying at x equals 1, the y value is about here. So if we are kind of following the graph on both the left and the right sides going towards x equals 1, we're basically saying what y value is it. So at that point, it looks like the y value is -2. So the limit there is -2. And as you can see, the limit there is an actual point there. So it's a little bit more obvious. But then this next one, if I'm looking at the limit as x approaches 3, at x equals 3, there's a hole right there. But it doesn't even matter whether a point there exists or not. As long as your graph is approaching a certain y value, then that counts. So at x equals 3, the y value looks to be 0. So that would be the limit. So it doesn't matter whether there's a point there or not. So the other way I want to talk about finding limits is numerically. So numerically means you don't have a graph to look at. So looking at this next equation, we have f of x equals x squared minus 3x plus 2 divided by x minus 2. No graph for you. And you can graph if you really want, but I'm not trying to make you graph a whole bunch. So with numerically, all we're doing is basically, like without the graph, we're just going to make our own XY chart, because then we can figure out like what numbers does it get close to, and then we can kind of tell. So what I'm going to do is just kind of set up a little table of values or XY chart, whatever you want to call it. And in order to find a limit, let's say we're trying to find the limit as x approaches 2 of this function, f of x. Okay. So if I want to know what the y value is at 2, then we just need to plug in values that are close to 2 so that we can kind of tell what y value it's going to get close to. So I don't know what's at 2, but I'm going to choose some numbers that are smaller than 2, bigger than 2, but generally like closer numbers. So maybe like 1.99, 1.9, maybe 1, and then on the other direction, maybe like 2.01, 2.1, 3 maybe. So at this point, we're just plugging in those numbers into the f of x function. So after plugging in my numbers into the f of x, these are the numbers I got for the y values. So taking a look at when x equals 2, then it looks like the numbers are getting close to 1 as you approach 2 on both sides. So safe to say that the limit as x approaches 2 of f of x is going to be 1. So using the same function as before, I'm going to do another example. So if we're trying to find the limit as x approaches 3 this time of f of x, so the same f of x as before. This time, rather than doing the entire chart right here, at x equals 3, when I plug it into the function itself, I actually get an answer from this, so without actually having to do the whole chart, because before, when I was looking for the limit as x approaches 2, I couldn't just plug it in because I ended up getting 0 on the bottom of the fraction. And remember that rule where you're not allowed to divide by 0? That's why I had to do this whole chart way. So if you don't end up breaking any rules, like dividing by 0 or something like that, when you plug in x equals 3, then you can just plug in. So when I do this, I end up with just 2. So by doing that, because I can just plug in, I don't have to do a whole chart. But if I end up plugging in and ending up dividing by 0 or something, then I have to do the whole chart with trying to see where the y value ends up. Because if you end up dividing by 0, it's usually a case where in the graph, if we were to graph it out, there would be a hole in it. And so there isn't an actual point there. Kind of like how we were looking at the graphs earlier. Like for this first example that we did graphically, at x equals 1, when I plug into my equation, I end up dividing by 0 because I end up with 1 minus 1 on the bottom, which is 0. So that ended up with a hole there, and so if I were to plug in, I wouldn't get anything, but looking at the graph, I can tell it gets close to the number 3 as the y value. So that's what we're basically looking at here. So the last thing I want to talk about today is, when does the limit not exist? And this might sound familiar if you've ever watched Mean Girls, because, you know, it's like a very popular quote, the limit does not exist. And so there's actually 3 rules for when this would occur. The first one is when the limit approaches a different number on the 2 sides. So for example, if we're looking at this function here where f of x is the absolute value of x divided by x, when that's the case, the absolute value of x is always going to be a positive number, and then you're dividing by x, which could be a positive or a negative number, but anytime you divide that, you end up with 1 or negative 1, depending on whether x is a positive or a negative number. So on the right side of the graph, since x values here are all positive, you have a positive number from the absolute value divided by a positive number, gives you a positive 1. But on the left side of the graph, you have a positive number on top because of the absolute value dividing by a negative number for x, which gives you a negative 1. So in this case, as we approach x equals 0 on both sides of the graph, you end up getting towards 2 different numbers, because on the right side, it's approaching positive 1, on the left side it's approaching negative 1. So because the limit approaches 2 different numbers from the left and right sides, this is a time when the limit does not exist. So we just write D and E to stand for does not exist. Okay, the second rule for when a limit does not exist is when the limit approaches infinity or negative infinity. So basically not a specific number. So limit, when we answer like what is the limit, it has to be an actual number. So if it's not an actual number like infinity or negative infinity, then it would not exist. So like in this graph here, if we're looking at the limit as x approaches 0, so we're looking at coming towards 0 on both sides, both the graphs keep going up and up and up forever and ever. So because that doesn't approach an actual number, then again, this limit here does not exist. And the last rule is when the limit oscillates, or like it's switching between 2 different values. So like in this example here, we have the function f of x equals sine of 1 over x. So this is the graph that it makes. It looks kind of crazy. So if you think of the regular sine graph, it just like goes up and down like this with the waves, right? But when we're dealing with like sine of 1 over x, the weird part is as you get closer to x, your like waves get really, really like squished together. So it just looks really weird. But because of this, if you think back to your regular sine wave, the highest it goes is 1 and the lowest it goes is -1, and it just switches between those two values and everything in between, right? So when we're talking about this graph here, we know the highest it's going to get is 1, the lowest it's going to get is -1, but it keeps switching between those two values, so we'll never know as you get closer and closer to x equals 0 what the actual number is going to be, because this does get squishier and squishier forever and ever. So because of this, this limit also does not exist because it's switching between 1 and -1. So those are the rules for when a limit does not exist, and now you know how to find limits graphically and numerically. Thanks for watching, guys. Bye!